Hi. Now in today's lecture we will look at the structure of alcohols and phenols. Basically how structure of alcohol phenols looks like. And we already know that both alcohols and phenols contain OH group, right? In phenols this OH group is attached directly to the benzene ring, right? And in alcohols this OH group is attached to the alkyl groups, right? So we'll also be looking at how this alkyl group or this benzene ring can affect the properties of alcohols and phenols, right? Let's draw it this way. This is your benzene, right? This is how phenol looks like, right? Where OH is directly attached to phenol. OH is directly attached to this benzene ring. Whereas let's take simple alcohol, let's say methanol, right? Here this OH is attached to this methyl group, right? Now when we talk about structure, right? When we talk about structure of any compound, we would be looking at its hybridization that we have learnt in chemical bonding. We would be looking at its bond angle, and then we'll be looking at its bond length, right? These kind of things we will be looking into the structures. Then we'll see how all these things would affect the reactivity of compounds, right? So basically this is your structure and reactivity study, right? So let's look at the hybridization of oxygen atom first. Basically your oxygen atom, oxygen is sp3 hybridized, right, in both your phenols and your alcohols. And we know that electronic configuration of oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1, right? The first step towards to know hybridization is to write the electronic configuration. Now we know the electronic configuration, right? Now in hybridization, these three orbitals, 2s and 2p orbitals will undergo mix and merge, right, to give you a set of 4 sp3 hybrid orbitals, right? Because if you remember from chemical bonding, the number of hybrid orbitals formed is equal to the number of atomic orbitals that are getting that are mixing up, right? Here you have 1, 2, 3, 4 atomic orbitals, 1 2s and 3 2p orbitals are mixing and merging, right? So they will give rise to 4 equivalent set of orbitals, which are your 4 sp3 hybrid orbitals, right? So you can see from here, when these merge, 2 of these orbitals contain lone pair of electrons, so they will not take part in bonding, whereas these 2 contains your single electrons. They are singly occupied, so they will react so that they can get 2 electrons, so that they can make 2 electrons, they will react, right? So this is how oxygen will look like. These are these 2 sp3 hybrid orbitals that contain these 2 lone pairs, right? Then you have these, this is 2py, this is 2pz, it has 1, it has 1, right? This is your oxygen atom, right? This is the hybridization of oxygen atom in both phenols and alcohols, right? So this is your sp3 hybridized. Now since I said only these two orbitals, these 2 sp3 hybrid orbitals, now these are no longer 2py or 2pz, but these are sp3 hybrid orbitals. These are 2 sp3 hybrid orbitals that contains these are lone pair of electrons, right? And these 2 will react, right? And they will form bond pair of electrons, if you remember from your chemical bonding study. So these 2 will form bond pair of electrons, right? Now let's look at here. Let's look at this part of alcohols and phenols. Right? We know that in benzene, if you know the structure of benzene, these are carbon atoms. All these carbon atoms are your sp2 hybridized. This is sp2 hybridized. This is sp2 hybridized. So this carbon atom to which this O is connected, this is also sp2 hybridized. Right? And in methyl, your carbon atom is sp3 hybridized. Right? This is sp3 hybridized. This is sp2 hybridized carbon atom. So this is the difference in alcohols and phenols in their structure, that the carbon atom to which oxygen of OH is attached in alcohols is sp3 hybridized, right? Whereas the carbon atom to which oxygen of OH is attached in phenols is sp2 hybridized, right? So now let's draw it over here. This is your oxygen, right? These two sp3 hybrid orbitals contain lone pairs, right? And this is your sp3, two sp3 hybrid orbitals that contain singly occupied electrons. Now, in this structure, this is your sp2 hybrid orbital, right? Which will, because we know that when bonding takes place, it is basically the overlapping of orbital that is happening. So we will be looking at when this carbon of benzene, right, will form bond with this oxygen of OH, what type of orbitals are involved. Right? Now, since we said that oxygen is sp3 hybridized, it has two orbitals that will take part in bond formation. Right? So when this CO bond will form, right, when here this CO bond will form, we know that oxygen is sp3 hybridized. So one of its singly occupied orbital, like this is oxygen, one of its singly occupied orbital, right, will overlap with sp2 hybrid orbital, like this, sp2 hybrid orbital of carbon atom. Right, this is sp2 of carbon and this is sp3 of your oxygen atom, right, to form this carbon oxygen sigma. Right? Now we have one more sp3 hybrid orbital, right? And if you see here, from this side it is forming bond with your carbon atom, and from here it is forming bond with hydrogen atom, right? And we know that the electronic configuration of hydrogen is 1s1. There is only one electron which is in s orbital, right? So this s orbital electron will try to gain stability by forming bond, right, with oxygen atom by sharing its one electron, right? So it will share one electron from oxygen atom and it will form it will pair up, right? Now it will have two electrons. So here this sp3 hybrid orbital, right, will form bond with, say, this sp2 hybrid orbital of your benzene ring, right? This is, I've just reversed the direction, and this is your sp3 hybridized. This is your sp3 hybrid orbital of oxygen. This is sp2 hybrid orbital of your carbon atom, right? Now this is the other sp3 hybrid orbital that can take part in bond formation. So this bond, OH bond, right, will form by overlapping of sp3 hybrid orbital of oxygen, right, with your 1s orbital of hydrogen atom, right? So it will happen like this. This is your orbital of hydrogen atom, 1s orbital. So now this 1s orbital will overlap with sp3 hybrid orbital. So now we have two bonds, sp2 carbon and sp3 of oxygen, to form carbon oxygen sigma bond, right? And here you have this bond, sp3 of your oxygen, right, will form bond with 1s orbital of hydrogen to form OH sigma bond. Right? sp3, just look at the overlapping. sp3 orbital of oxygen will overlap with 1s orbital of hydrogen atom to form this OH bond, right? And sp2 hybrid orbital of benzene carbon will overlap with sp3 hybrid orbital of oxygen atom, right, like this, to form CO sigma bond. This is how bonding takes place, right? So if we just, and these two are lone pair, right? And we know that sp3 hybrid orbital, it has tetrahedral shape, right? Now let's look at it about regarding its bond angle, right? In alcohols, this is R, this is O, this is H, right? And it has these two orbitals that has lone pair of electrons, right? These two orbitals. Now this angle should be 109.5, right, which is the tetrahedral angle, but it is observed the angle is 105, right? The angle is 105 degree. What could be the reason? The reason is, we know that lone pair repulsion is greater than lone pair bond pair repulsion, and this lone pair bond pair repulsion is greater than bond pair repulsion, right? So you have maximum repulsion between lone pair. That means these two will repel one another, right? These two, right, since they are lone pair of electrons, these two will repel one another and they will decrease this bond angle, right? They will decrease when they repel one another. They will press these orbitals closer, so they will decrease this 109 angle to 105. So this angle is 105, right? Why? Because of your lone pair repulsion, right? So bond angle reduces to 105, then normal tetrahedral angle due to lone pair repulsion, right? Due to lone pair repulsion, it will reduce further, right? Now let's now look into other properties, right? Or let's first look into the effect of methyl group and effect of this benzene ring, right, on the structure of alcohols and phenols, right? Since we know that benzene is, and this bond is polar bond, right, because of difference in electronegativity, this bond pair would be more towards oxygen, giving it slight negative charge, and hydrogen will acquire slight positive charge. This is how it looks like. Here also, sorry, it will have negative, it will have positive, right? Now this is your benzene ring. We know that benzene ring is electron withdrawing, right? So it will withdraw electron of this oxygen, right? When it will withdraw electrons of this oxygen, it will reduce the negative charge on oxygen, right? So your benzene ring, benzene is electron withdrawing, and will reduce negative charge on oxygen of OH, right? If we talk about this, phenol, in phenol your methyl is electron releasing. This is electron attracting benzene, whereas methyl is electron releasing, right? So it will intensify the negative charge on oxygen atom, right? The negative charge on oxygen atom is intensified because of electron releasing nature of methyl group, right? So your methyl group is electron releasing and will affect some properties, right? Your methyl is electron releasing and will intensify negative charge on oxygen of OH bond, right? Just remember what these two things, these two, benzene and methyl, do, right? Their behavior, electron withdrawing, and this is electron releasing. So electron withdrawing effect will intensify, electron withdrawing effect will reduce negative charge on oxygen atom, it will disperse negative charge, whereas methyl will intensify the negative charge on your oxygen atom of OH, right? Now, due to this, dipole moment of phenol is lower than that of methanol, right? Dipole moment of phenol, we say dipole moment of phenol is less than the dipole moment of your alcohol, say methanol, right? Why? Because you have less charge now on this oxygen atom, right? Less charge means less dipole moment. Now this bond is less polarized, that means, right? And we know that dipole moment depends on the polarity. The more the polarity, the more is the dipole moment. So when this withdraws electron, it is making it less negative, right? Less negative means the bond will become less polar, right? That will reduce its dipole moment. Whereas in case of methanol, it is reversed. It is intensifying this charge on, negative charge on oxygen atom, due to which it will acquire, due to which the dipole moment would be higher for methanol, right? So this is important, right? Why the dipole moment of phenol is less than that of phenol, right? The simple answer would be that negative charge on oxygen is reduced due to electron withdrawing effect of benzene, right? Whereas in methanol, it is increased due to electron donating effect of methanol, right? I hope this is clear. Now, we will be looking into some more properties, right, based on the structure, right, based on the structure. One more thing, if we talk about the bond length, right, bond length of CO in alcohol and bond length of CO in methanol, right, bond length of the CO bond length in methanol, right, here the CO bond length in methanol, right, this bond length in methanol is 142 pm, whereas CO bond length in case of phenol is 136 pm. This is very important. Why bond length of CO is less in phenol compared to that in phenol, although both are CO bond, but why it gets reduced in phenol? The reason is, we know that oxygen has lone pair of electrons, right? If we, let me just show it. Right, you can take this down. Right, if we look at this phenol molecule, right, the lone pair on oxygen atom enters into resonance or conjugation with this benzene ring, right? When it enters into conjugation with the benzene ring, what happens is a slight double bond will get developed. A slight double bond will get developed on your phenol molecule, right? Since we know that double bonds are shorter compared to your single bonds. That is why this bond is shorter. This is 136 pm, whereas if we talk about this molecule, methanol, it is 142 pm. Right? This is very important. The simple reason is why the bond, if the question comes why the bond length of CO is less in phenol than in methanol, the reason is that the lone pair of electron on the oxygen atom of phenol enters into conjugation with the benzene ring, right? We know that this benzene is already conjugated, right? So this lone pair will enter into conjugation with this phenol, with this benzene ring, thereby developing a slight double bond character, a partial double bond character, right? So CO bond will develop a partial double bond character, due to lone pair of oxygen atom entering into conjugation with the benzene ring. Right? I hope this is clear. Right? Now, there is one more thing regarding the acidity of your alcohols and phenols. We know that phenols are more acidic than alcohols. Right? If you look at its structure, why alcohols are more acidic than phenols? Phenols are more acidic than alcohols. Right? Phenols are more acidic than alcohols. Right? What could be the reason that phenols are more acidic than alcohols? The reason is, if you look at the structure of phenol, right? In phenol molecule, when we talk about acidity by simple definition means release of hydrogen ions, right? So when you add phenol to water, it will form phenoxide ion, right? This is your phenoxide ion plus hydrogen ions, right? It is due to these hydrogen ions that your phenol says it is acidic. Whereas if we talk about methanol, when dissolved in water, it will form methoxide ion and your hydrogen ion. Right? One important thing to consider here is that this phenoxide ion is stable due to resonance. Right? We know that this lone pair of electrons, as we have learned here, right, why the bond length of CO is less in phenol. Similarly, when this lone pair of electrons enter into conjugation with this benzene ring, what is happening is, when there is resonance getting developed in the molecule gets more stable, right? So phenoxide, let me just write it down. This is your phenoxide, right? Your phenoxide, your phenoxide is more stable due to resonance, because the lone pair of oxygen enters into conjugation with the benzene ring in phenoxide ion. That makes it more stable. Since it is more stable, right, phenol exists as phenoxide ion, right? So it has more hydrogen ions. Whereas if we talk about methoxide, there is no resonance, this is less stable. Right? Since this is less stable, this forward reaction, due to which this is acidic, in forward reaction you have these hydrogen ions, right? So this methoxide ion, since they are less stable, so they will react with hydrogen ions to form back methanol, right, in this direction, reverse direction. So reverse reaction is favored because your methoxide is less stable. So it immediately combines with hydrogen ion to form methanol. Whereas in case of phenol, this phenoxide is stable due to resonance, right, because the oxygen atom, lone pair on oxygen atom, enters into conjugation with the benzene ring, right. So since it can exist as phenoxide ion, so you have more hydrogen ions in case of phenol, which makes it more acidic, right. So that is why we say the phenol is more acidic compared to your alcohols, right. I hope all this is clear, right. Just remember the structure that we have discussed earlier, that oxygen is sp3 hybridized, right. These two are lone pair of electrons, these are singly occupied or with singly occupied hybrid orbitals, which will enter into bond formation with your benzene ring or methyl and the other oxygen atom, right. So due to these lone pair of electrons, the bond angle will reduce from normal tetrahedral angle to 105 degree in your alcohols, right, and phenols. The bond angle reduces in phenols and alcohols because of lone pair repulsion. Lone pair repulsion is more maximum, so it reduces the normal tetrahedral angle. Now the other thing is, benzene is electron withdrawing in nature, whereas methyl group is electron releasing in nature. So methyl group will increase negative charge on oxygen atom, your benzene will reduce negative charge on oxygen atom, due to which dipole moment of phenol is less compared to that of methanol, right. Now talking about the bond length, the bond length, CO bond length in phenol is less compared to the CO bond length in your methanol or alcohols, right. Why? Because the oxygen atom on because of the lone pair of electrons on oxygen atom enters into conjugation with the benzene ring, right, due to which it will develop a partial double bond character, and we know that double bonds are shorter compared to single bonds, right. And coming on to the acidity, phenols are more acidic than alcohols, again because since when you suppose you add phenol to water, it will be more acidic. Why? Because of this reaction, because the forward reaction is favored. Why? Because your phenoxide ion is more stable. Why it is more stable? Because the lone pair on oxygen enters into conjugation with or resonance with the benzene ring, that makes phenoxide ion more stable. So you have more hydrogen ions in phenol compared to in methanol. In methanol, this methoxide ion is not stable, so it immediately combines with hydrogen ions to give you back methanol, right. So backward reaction is favored, reverse reaction is favored, so you have less hydrogen ions in case of alcohols or here methanol. So phenols are more acidic than alcohols. I hope all these things are clear. Thanks.